Today we'll see two types of satellite. One is the geostationary or the geosynchronous satellites. A satellite which appears to be at a fixed position at a definite height, that is stationary to an observer on Earth, is called geostationary satellite. That means एक सैटेलाइट जो हमेशा किसी ऑब्जर्वर को अर्थ की पोजीशन से स्टेशनरी दिखाई देता है, ऐसे सैटेलाइट्स को हम जियो स्टेशनरी सैटेलाइट्स कहते हैं. दिस सैटेलाइट इज ऑल्सो कॉल्ड एज जियोसिंक्रोनस सैटेलाइट as the angular speed is synchronized with the angular speed of the earth about its axis. इस सैटेलाइट्स को हम जियो सिंक्रोनस सैटेलाइट्स भी कहते हैं क्योंकि इसकी जो एंगुलर स्पीड होती है, मीन्स जिस स्पीड के साथ सैटेलाइट रिवॉल्व करता है अपने ऑर्बिट में, उसी अर्थ की स्पीड के साथ वो सिंक्रोनाइज करता है. मतलब अर्थ की स्पीड के साथ ही उसकी भी एंगुलर स्पीड होती है सैटेलाइट की. So that's why these satellites revolve around the earth with the same angular speed in the same direction as is done by the earth around its axis. So obviously the speed of such a satellite relative to earth is 0, and that is why it appears to be stationary with respect to any point on the surface of earth. Clearly we know that t is equal to 24 hours. So for this satellite, what would be the height? Because the time period for these satellites to revolve around the earth in a equatorial plane is 24 hours, and that is same as for the angular the time period for the earths to rotate on its axis. So t is equal to 24 hours. We know the formula of height, altitude, that h equal to t square r square g upon 4 pi square, the cube root of this quantity, minus r. So when we put the value that t is equal to 24 hours or t is equal to 24 into 60 into 60 seconds, and the radius of earth is 6.4 into 10 to the power 6 meter, acceleration due to gravity 9.8 meter per second square, then we'll calculate by this formula the value of height or the altitude will come, that is 3.6 into 10 to the power 7 meter, or we can say 36,000 kilometer. And when we calculate the orbital velocity or the speed, that will be equal to 3.1 kilometer per second. This is the orbital speed of this satellites, geostationary or geosynchronous satellites. Geostationary satellites are used for the purpose of communication, and therefore they are called communication satellites. INSAT 2B and INSAT 2C are the communication satellites of India. Here we'll see some essential condition for geostationary satellite. The first condition is a geostationary satellite should be at a height nearly 36,000 kilometer above the equator of earth, and its period of revolution around the earth should be same as that of earth about its axis, that is exactly 24 hours. Third, it should revolve in an orbit concentric and coplanar with equatorial plane. You can see that the geosynchronous satellites, this is the earth and this is the equatorial plane of the earth. So the geosynchronous orbit is here, that is this orbit will be means it should you can see the concentric circle is there, this equatorial plane and this orbit if you observe. So it should revolve in orbit concentric and coplanar. You will see that concentric, the center of this equatorial plane, and this orbit must be same, and the plane of this equatorial plane and this orbit would be same. So these are concentric and coplanar with the equatorial plane, and so the plane of orbit of the satellite is normal to the axis of rotation. This is the axis of rotation. So this orbit or the plane of this orbit is always perpendicular to the axis of rotation. This is the axis of rotation and this is the plane of orbit in which the satellite revolve around the earth. Okay, so next point is the angle between equatorial plane and orbital plane of geostationary satellite is 0. You can see that equatorial plane and this orbital plane of this satellite. These are in the same plane because these are coplanar, so the angle between this plane would be 0. Next is its sense of rotation should be same as that of the earth about its own axis, and that is from west to east. Its orbital speed is nearly 3.1 km per second. Polar satellites. These are those satellites which revolve in polar orbit around earth. A polar orbit passes over both north and south geographical poles, and once per orbit it is also called sun synchronous satellites. It is important to note that a single polar satellite can monitor 100% Earth's surface. Every location on Earth lies within the observation of polar satellites twice each day. The polar satellites are not used for communication purpose but are used for the remote sensing, and important uses of polar satellites we will observe here. That is the first in forecasting weather, second in survey of groundwater, third in detecting area under forest, fourth for assessment of drought, fifth in preparing wasteland maps, sixth in the assessment of crop disease, next detection of good fishing zones in river or ocean, and for the spying purpose, that is to locate the position and movement of the enemy troops, in studying upper region of atmosphere, and in location of place and time of nuclear explosion is conducted. Here you can see that about the polar satellites, it revolve around this orbit. As you can see here, this orbit passes through the both the poles, north and south pole, and you know that when this is orbiting around this orbit, okay, means orbiting around the earth in this orbit, so you will find that after some time the earth will spin on its axis from west to east direction. So in 24 hours you will see that this means plane will be monitoring 100% of earth's surface. So that's why, and this plane is you will see that when it is passes through equator, so this will be, that's why when it is passes through equator, so it will face, that means the sun portion, and that's why it is called the sun synchronous satellites also. Okay, so that is about the polar satellite. Now we'll see weightlessness. It is a situation in which the effective weight of body becomes zero. When effective weight of body becomes zero, actually it is what, the effective weight of body, that is mg, it becomes zero. So that is called the situation of weightlessness, and this will arise when body is taken at center of earth. That is, when body is taken at center of earth, g is equal to 0, and because g is equal to 0, mg is equal to 0. Mg is weight and weight is 0, so the means the observer can feel the weightlessness, or you can see that means no weight measured by the weighing machine in that situation. So this is the case of weightlessness. Next you will see when body is taken at null point. Null point, that means at that point where you will find all the gravitational force due to different masses cancel out. So that is also means because at that point all the gravitational force due to different masses cancel out, that means no net gravitational force is there, and because no net gravitational force is there, obviously the gravitational pull will be 0 in that situation, or you can say mg is equal to 0. So that is also a case of weightlessness. Next we'll see when body is lying in freely falling lift. So this case we have already observed in chapter 5, laws of motion, when the body or when a lift is freely falling. In that situation the formula came that g dash is the appear, means the acceleration due to gravity which appears, or the apparent acceleration due to gravity you can say, and that is equal to g, that is actual acceleration due to gravity, minus the acceleration by which this lift is falling. So here the lift is falling because of the means free fall is there. So in free fall situation, the acceleration which produce on this lift is also g, so a become g here, and in that case g minus g will come 0, so g dash will, that means the apparent acceleration due to gravity is equal to 0, and because of that mg dash would be also 0. So the weighing machine will not measure any of the weight, that means the person will feel weightlessness. Okay, next we will see when the body is inside a spacecraft or satellite which is orbiting around the earth. In that case also we'll find here that the weightlessness situation would be there. Okay, so these are the some conditions, and you will find that in the top end of the balance is no longer fixed to the top ceiling of the room, then both the spring as well as object will move downward with same acceleration, that is acceleration due to gravity. In that situation when we are measuring the any object with the spring balance, so spring balance and the that top of the ceiling of the room, in case of free fall, that is the top of the ceiling of the room also will be moving with same acceleration, and that case also, that is the acceleration due to gravity, in that case also will find the no weight will be there. In this situation the spring is not stretched and no upward reaction force acts on the object. Now the reading recorded by the spring balance is 0 and the observed weight of the object is also 0. It means the object is weightless when it is free fall. And in satellite situation already we have seen, when a satellite is orbiting around the earth, then satellite and every object inside the satellite has an acceleration equal to the acceleration due to gravity and directed towards the center of earth. It means it means every object inside the satellite is in a state of free fall. This already we have discussed when we were looking the principle of launching of satellite. So once a condition come in which when we are throwing any of the object or the satellite in a means horizontally with some speed, so we see that the satellite will be setting in the orbit, and that is called the orbital velocity. So with that orbital velocity the satellite is always in free fall situation. When it always in free fall situation, then g would be 0, and g would be 0, so whatever the object or the means whatever the things are inside the satellite will also feel a state of free fall, and it is similar to the state when the object is falling freely towards the earth from a height, and therefore the object inside the satellite experience no gravity, and that is why the object in a satellite orbiting around earth is in weightlessness state.